Imagine a world beyond our everyday experience, a realm where space itself takes on an entirely new dimension. We live in a universe defined by length, width, and height, but what if there's more? What if our reality is just a slice of something far grander? This isn't science fiction, it's a profound concept explored by mathematicians and physicists for centuries. Understanding the fourth dimension challenges our intuition and expands our perception of existence. It forces us to think in ways our brains aren't naturally wired to comprehend. Let's start with what we can easily grasp. A zero-dimensional object is simply a point, with no size or extent. It exists only as a location. Now, extend that point in one direction, and you create a line. This is a one-dimensional object, possessing only length. A being living on this line could only move forwards or backwards. If you take that line and extend it perpendicular to itself, you form a flat surface, like a piece of paper. This is a two-dimensional object, having both length and width. A being in this flat world could move left, right, forwards, or backwards. Finally, extend that flat surface perpendicular to itself, and you create a solid object. This is our familiar three-dimensional world, possessing length, width, and height. We can move in any direction, up, down, left, right, forwards, or backwards. Now, for the mind-bending part, what if we extend a three-dimensional object perpendicular to all three of its existing dimensions? This is the conceptual leap to the fourth spatial dimension. It's not a direction we can point to in our world. Think of it this way. A two-dimensional being, a flatlander, would only see a cross-section of any three-dimensional object passing through their world. If a sphere passed through their plane, they would first see a point, then a growing circle, then a shrinking circle, and finally, another point. They would never perceive the sphere's full three-dimensional form. Similarly, if a four-dimensional object were to pass through our three-dimensional space, we would only perceive its three-dimensional cross-sections. We would see a series of changing three-dimensional shapes, never the complete four-dimensional entity. Our brains are simply not equipped to process that extra spatial axis directly. When we talk about the fourth dimension, it's crucial to distinguish between two main interpretations. The most common and intuitive one for many is time. In physics, particularly in Einstein's theory of relativity, space and time are interwoven into a single four-dimensional fabric called spacetime. Every event in the universe can be described by four coordinates, 3 for its position in space and 1 for its position in time. This means that to fully locate something, you need to know not just where it is, but also when it is. This concept revolutionized our understanding of gravity and the universe. However, there's also the concept of a fourth spatial dimension, which is what we've been exploring with the analogies. This is a purely mathematical construct, an additional direction perpendicular to length, width, and height. While we can't experience it directly, we can describe it mathematically and explore its properties. Since we can't directly see a four-dimensional object, how do we even begin to visualize it? We rely on projections and analogies. Much like a shadow is a two-dimensional projection of a three-dimensional object. The most famous example is the hypercube, also known as a tesseract. A tesseract is to a cube what a cube is to a square. Just as a square is formed by moving a line perpendicular to itself, and a cube by moving a square perpendicular to itself, a tesseract is formed by moving a cube perpendicular to itself in a fourth spatial direction. When we see a tesseract depicted, we are usually looking at a three-dimensional projection of it. It often appears as two nested cubes, with all their vertices connected. As it rotates in four-dimensional space, its three-dimensional projection would appear to morph and change in complex ways, revealing different aspects of its true form. This rotation is key. Just as a 3D cube rotating casts a changing 2D shadow, a 4D hypercube rotating casts a changing 3D shadow, or projection into our space. These visual representations help us grasp the mathematical relationships, even if the full object remains beyond our direct perception. The concept of higher dimensions isn't just a mathematical curiosity. It has profound implications in various fields. In physics, as mentioned, spacetime is a fundamental four-dimensional construct. Understanding it is crucial for comprehending phenomena like black holes, the expansion of the universe, and the nature of gravity. Some advanced theories, like string theory, propose the existence of even more spatial dimensions, perhaps 10 or 11 in total. These extra dimensions are thought to be compactified, or curled up so small that we cannot perceive them directly, much like a garden hose appears one-dimensional from a distance but is two-dimensional up close. Beyond physics, the idea of higher dimensions is used in data science and computer graphics. When dealing with complex datasets, each variable can be considered a dimension. A dataset with hundreds of variables exists in a high-dimensional space, allowing algorithms to find patterns that are invisible in lower dimensions. In computer graphics, techniques are used to project higher dimensional data onto our 2D screens, creating realistic simulations and virtual environments. While not truly four-dimensional, these applications demonstrate the power of thinking beyond our immediate spatial limitations. Exploring the fourth dimension, whether spatial or temporal, pushes the boundaries of human thought. It challenges our ingrained perceptions and forces us to consider realities beyond our immediate experience. It's a testament to the power of abstract reasoning and mathematical modeling. This journey into higher dimensions isn't just about understanding the universe. It's about understanding the limits and potential of our own minds. It teaches us that what we perceive as reality might just be a small part of a much larger, more complex tapestry. By grappling with these abstract concepts, we develop critical thinking skills and an appreciation for the elegance of mathematics. It opens doors to new scientific discoveries and technological advancements, inspiring future generations to question, explore, and innovate. The universe is far stranger and more wonderful than we can imagine, and the fourth dimension is just one glimpse into its incredible complexity.